Hello everyone. Thank you all for joining us today. My name is Tim Bruns. I am the Associate Editor of Roads and Bridges magazine. On behalf of Roads and Bridges and our sponsor, MISTRAS, I'd like to welcome you to today's presentation titled, How to Utilize Long-Term Structural Health Monitoring Systems to Reduce Costs and Prevent Catastrophic Damages. MISTRAS industry experts will discuss implementing a long-term unattended structural health monitoring system, which includes reducing bridge maintenance costs, enhancing bridge safety, prolonging bridge lifespan, utilizing acoustic emission for SHM system case studies. This webinar is ideal for bridge owners and maintenance management personnel of suspension, cable stay, pre-tensioned, post-tensioned, concrete, and steel bridges. We're going to get started in just a couple of minutes, but first, a little housekeeping. You will notice on your viewer that you have the ability to ask questions. We encourage you to ask questions, and we'll try to answer as many as we can at the end of the presentation based on time availability. Any questions we do not get to, we will answer offline. Participants in today's webinar earn 1 professional development hour. I will give you directions for receiving your certificate at the end of the webinar. For those of you viewing as a group and wishing to receive a certificate, please download the multiple viewer sign-in form you will find on the Resources tab of your viewing console. Follow the instructions to receive your certificates. Also available in the Resource tab for downloading is a PDF of this presentation. Our first presenter is Richard Gastautis, MISTRAS Group's Technical Support Manager for Infrastructure, and John Watson, Infrastructure Sector Lead for MISTRAS Group. Richard is responsible for the implementation of non-destructive testing and evaluation services and structural health monitoring for civil infrastructure. Richard has been using acoustic emission and other technologies for nearly 20 years, with an emphasis in the development, implementation, and deployment of integrated systems. Mr. Gastautis has hands-on experience in field installation, testing, training, monitoring, on-site support, analysis, and commissioning of remote online monitoring systems for buildings, bridges, offshore oil platforms, wind turbines, and marine vessels. Richard is the current ASTM Subcommittee Chairman of E07.04, Acoustic Emission, and is the Membership Secretary for ASTM Committee E07, Non-Destructive Testing. Richard graduated from the University of Kansas with a BS in 2000 and MS in 2004 in Civil Engineering. John Watson is the Infrastructure Sector Lead for MISTRAS Group. He joined MISTRAS after completing industrially sponsored postgraduate research in structural health monitoring in 1998. He has led the development and delivery of specialty NDT and monitoring solutions for a variety of bridge issues, including the detection and management of hidden defects. And now I will turn it over to Matt Costello for his introduction.
Thanks, Tim. So what we're going to do today is run you through a presentation here. We're going to give you a background on MISTRAS as a company, who we are, what we do, some history and facts about the company, and our one source, one solution, which combines our products, services, and software as a single provider. Then we're going to run you through our technology, instrumentation, sensors, necessary equipment, how it's used, and we have some example drawings for you as well. Acoustic emission. So it's a short, rapid release of energy in the form of a transient elastic wave. We're going to run you through the basic technical concepts. Then we're going to wrap it up with some really great case studies and then some Q&A at the end. So some quick facts. We're founded in 1978, actually celebrating our 40th year in business this year, and we're headquartered in beautiful Princeton Junction, New Jersey. We have over 7,000 employees spread out over 120 locations worldwide. And what does this mean? It means if you have a bridge monitoring project, whether it be on the East Coast, the West Coast, Canada, the UK, we're going to have a local lab close by to address any issues that could arise. And this is something that our competitors, they don't have that capability that we offer. And that's what we call our local presence, global reach. Also, we have the experience. Our first monitoring project was in 1972. the Dumbarton Bridge in San Francisco. We've been doing this a long time, and we have the capabilities. For example, the San Francisco-Oakland Bay Bridge, we're monitoring over 20,000 feet of IBAR, roughly 3.2 miles. And we're also excited to officially be a part of the George Washington Bridge Rehabilitation Project. It's the world's busiest motor vehicle bridge, and we're going to be monitoring the main suspension cables as well as the New York and New Jersey anchorages. So this is what we call our one source, one solution approach. It's a unique combination of products and technologies, 24/7 online monitoring capabilities, and our non-destructive testing services, including drone inspections, rope access inspections, ultrasonics, GPR, and we combine this with our world-class enterprise-level data management and analysis software. So it's a comprehensive offering of products, systems, and services from one provider. Now I'm going to hand it off to our director, John Watson.
Hello, everyone. So when we started as a business in Princeton, New Jersey, we were very much a manufacturing company. So we started actually designing and manufacturing monitoring systems. Our original specialism is acoustic emission. And the next few slides show the progression of the state-of-the-art monitoring systems that we provide. So the slide that you see before you now is our current infrastructure workhorse acoustic emission system, which is called Sensor Highway. This typically has 32 channels for acoustic emission and 16 channels for alternative, more common sensors such as strain, temperature, displacement. But critically to bridge engineers, these systems are designed for practical use on-site industrially. So this is not an academic system. So it's very rugged. It's completely housed in a thick steel box with various options for different types of housing and protection. It's got a very high NEMA rating, which means it can survive fairly extreme temperatures and also weather and humidity. It's uniquely designed so it needs no separate cooling or heating, so you'll see no attachment of heat exchanger or air conditioning units. So it's a very practical system. The Sensor Highway 3 is in its third iteration now. It's been on bridges since about 2008, so it's the format or the concept is about 10 years old now, and it is still going strong with a variety of improvements inevitably over the years. So that's the kind of the main AE system that we use. So one of our unique selling points as a business is our history in acoustic emission. We're the worldwide leader in acoustic emission, and our founder, Sotirios Vahavalos, started with his research and R&D into the manufacture of AE sensors. So in the middle right-hand side, you can see a typical piezoelectric AE sensor. So it's about the size of a small chicken's egg. So it's not too small, not too large. We manufacture them in a variety of different casings for environmental protection. So the shiny one you can see is an unprotected normal one, and then the kind of the center right shows one in an environmental housing that allows both burial in concrete, but also exposure to rain, wind, and different types of humidity, which gives these sensors a very long lifetime. They're also completely housed to isolate them from different sounds, both airborne and also electric, such as EMI, RFI. We only detect what we want to. They come in a variety of different frequencies relevant to us, because that detects different sounds from different damage mechanisms from different materials, which we'll come on to in a short while. And then the sensor highway, it's called a highway because it's a gateway to collecting data from a variety of different sources. So one of the other common sensors that we use are weather sensors that enable us to correlate acoustic emission with different weather trends, whether it be wind speed, gusts, different types of precipitation, and also temperature, which obviously has a significant effect on structural movement and expansion and corrosion as well. So we very much originated and started in acoustic emission, but these days we have a much broader offering, recognizing the need for other information from other sensors that provide more quantitative data. So we have a suite of different systems, from the micro structural health monitoring system with just 4 sensors on the left-hand side, all the way through to small, medium, and extra large, topping out at 256 independent channels, which pretty much enables you an enormous amount of flexibility to make measurements on very large structures. And if you have a structure which is even larger, you can tether these together. So our largest is about 1,100 separate sensors, taking data from 5 of these large systems. They're typically designed not for ultra-high sampling rate. That's not really needed on bridge structures, so they go up to about 100 hertz sample rate. Typically, we operate at about 10 hertz for normal highway traffic. Again, very good environmental protection that enables these to last out on site for many, many years. And a full opportunity to connect virtually any sensor we like to these systems. It's very, very simple to connect up to design an instrument. So most of these sensors would be cabled. We use a technology common in the oil and gas and industrial industry called current loop, which enables us to run up to 1 kilometer of cable between a sensor with no additional power, which both carries a very small current and also the signal over the top. So these are all manufactured in our factory in Princeton, New Jersey. As part of the overall solution that we provide, we also provide power. Ideally, obviously, for long term, you want to connect to an AC supply, but if that's not available, we have solar, hybrid diesel, and also fuel cell solutions that enable these systems to run with, in many cases, no additional power or maintenance at all, almost infinitely, depending on your position on the globe. As with all systems these days, they're fully accessible, either by satellite broadband or 3G, 4G, and that enables you to connect to these systems whenever you want, but also to remove data and get the information that you need. So there's quite a few options, and we provide this as a kind of consultancy to recommend which system you need and why. So one of our latest innovations using micro technology is the new DAISY AE system. So this is about the size of a pack of playing cards, and it connects to 2 acoustic emission sensors. It uses a different type of network topography. So you connect one box to the next box via a Cat5 or a Cat6 cable. And this is ideally used for suspension bridges and long, thin structures. So this is what we've used on the George Washington project, which these systems are in manufacture now for that project. And these are designed to be installed at high level onto the main cable with the sensors spurred off them with a continuous Cat5 cable all the way along. The benefit is that it's a lot quicker installation, a lot less cable, which brings the entire cost of monitoring suspension bridge cables down substantially. So it's quite an innovative product. So the product side was very much where we started as a business, and the product side gives us a tremendous advantage because we can design and build hardware and software really to fit both the industry but also the solution. We're going to go on to show you some examples shortly. So the monitoring systems that we manufacture are very much focused on AE, damage detection, wire break, and structural health, with advanced capabilities to process this data, because this ultimately is what you need as a bridge owner, information about bridge performance, defects, and change. As Matt pointed out, we are a pretty vertically integrated company with a lot of different other skills as well, which complement the monitoring. So we carry out full visual inspections, a variety of different NDT testing, and specialist NDT as well, looking at a variety of different problems, corrosion and cracking. And that's not really covered in today's presentation, but we'd be happy to talk to anyone about that later. And then the final bit is our access capability. Having the monitoring systems is great and designing them, but we also offer a full installation service. So as you can see, one of my colleagues on the top left-hand corner is actually hanging on underneath that suspension cable, installing a sensor. So we do all the working at height and confined space installation as well, providing the full service. Okay, so one of the key points about the structural health monitoring that we have increasingly is the need to monitor structures continuously, and also the need to have continuous feedback and information. So MISTRAS has two global online monitoring hubs, one in the UK and one in Princeton Junction, where we have teams of engineers every working weekday on hand to do data analysis, reporting and system maintenance via a remote connection to some 200 different monitoring systems on bridges around the world and other structures. The need for online monitoring really depends on your structure and the condition and the problems that you're facing. So some of the common needs for online monitoring, which we'll cover hopefully in most of our case studies, is wire break of cables, whether that be in suspension bridges, cable stay or post tension, cracking in metallic structures, strain and fatigue measurements both in the short term and long term, a lot of bearing monitoring. One of the few replaceable parts of bridges, bridge bearing health, is increasingly topical, and there's significant issues if bearing health is ignored. Big integrated health, which is a variety of formats really, again, depending on the structural form, integration of acoustic emission, strain, tilt, GPS data, and corrosion. And then lastly, input from different processes and environmental, less driven by dynamic effects, but more environmentally driven things like cable corrosion, reinforcement corrosion, and measuring the impacts from the climate, which is particularly important, I know, in the US with the current hurricane, understanding the loading from weather events, but also global warming is going to become more of an issue as we need to understand how temperature change affects our structures and their behavior. So hopefully that was a short introduction to the services and products, and I'm going to hand you over now to Richard Gestastus to cover some of the case studies.
Thank you, John. I appreciate the introduction, and Matt, thanks for kicking things off today. So when we talk, as both Matt and John had mentioned, we've been an acoustic emission company since 1978. And the original founders of that company were actually engineers and researchers that started out with AT&T Bell Labs and Dunnigan Testing. And so since that time, we have been pushing, the envelope of acoustic emission and instrumentation for monitoring and other types of assets. We actually, one of the first solutions we provided was the local area monitor, which you could find in the old Bridge Inspection Reference Manual in Chapter 13. This was co-developed in 1995 with the Federal Highway Administration, and it was an 8-channel system that was developed with the intent of detecting cracking on steel bridges as part of this project. And under that project, we ended up doing 12 different bridges and was successful in detecting, cracking and monitoring existing cracks for ongoing propagation. And so it all comes down to, the question is, what is acoustic emission? Matt, kind of gave a definition earlier, but it's basically the short, rapid release of energy in the form of a transient elastic wave. And this energy is released, by a source that's in the material due to some type of degradation. So, when we're talking about bridges, we're looking at suspension bridges, post-tensioned or pre-tensioned bridges. We're looking for wire breaks that may occur due to degradation. Sometimes it's an issue with poor grouting, water gets in there, voids, and then just over time, these tendons start to corrode and start to break. And so that's one of the ways that we use acoustic emission for tracking that particular damage, over time. AE by itself is considered a passive technique. So once you install your sensor on the material or structure, we now use the loading of that structure to activate that potential source. So again, when we're talking bridges, we're looking at the traffic load, so your combination of cars and vehicles and overloads and permit loads provide the stress that may be necessary to, propagate, an existing crack or other type of discontinuity. And with the system that is going to be connected to the sensors are pulling in this information. So when you get that short rapid release of energy in the form of a mechanical wave, that transducer that's mounted to the surface then converts it into an electrical signal that we can measure. And so there's over 15 different types of AE parameters that we can measure from an acoustic emission signal. Some of the typical ones would be like, amplitude, energy, duration, rise time, and frequency centroid. And that information becomes important because when you're talking about bridges and other structures, there are different types of mechanisms. And those mechanisms often produce a different type of source. And so as we collect this information and collect this data, we've got a sister company in Greece that produces a software called Noesis, which is a neural network pattern recognition software. So it allows us to take in all of this data, particularly whether it's wire breaks or if we're doing pencil lead breaks. All of these have different types, and when it's run through this process, then the software can identify it into different classes. And so those different classes often represent a different type of mechanism. And so within our software, we have the capability in an algorithm that allows us to put in the proper components and parameters that we're looking for that particular type of application. So if we're looking for, cracking in steel, it will have a certain set of parameters that we're looking for. If we're talking wire break, it will have a different set of parameters. And so this system is automated to identify those particular mechanisms that we're looking for in real time. So, and one of these things that we look at is what's known as the absolute energy. So this is just a simple graph that shows you the magnitude of the different types of sources that you can find monitoring with acoustic emission. So on the low end, we have corrosion. So active corrosion for that's going on, whether it's some bridges, built up plates, which you may not be able to see that corrosion going on. Acoustic emission is a way to monitor that potential activity. And then as you get up to wire breaks, we're talking an order of magnitude difference. And so, this is very great when it comes to, suspension bridge cables as well as pre and post tensioned members. And of course, and one of the reasons that we use acoustic emission is that, we're monitoring and we're testing that structure, with stress. So, with that applied load, going across the bridge, that stress is what's ultimately going to activate that discontinuity. And depending on, what happens with it in the future, it could lead to failure. And so, AE, when you're talking about, that waveform, it senses movement of that crystalline structure. So it's not geometry, independent. And so that's kind of what makes it, a little bit different from, other methods that are out there. And the major benefit with acoustic emission is the fact that the sensor itself doesn't need to be next to the flaw. So, in one of these case studies, we were talking about the San Francisco-Oakland Bay Bridge, we had sensor spacings up to 50 feet, and we're still able to locate a crack anywhere along that 50-foot, linear range without having to be right next to, the source. And so basically, any AE test procedure that we have out there is, broken down into what we call, doing the setup, looking at the loading, and then, doing the evaluation and determining, what is that, AE source and where is it coming from. So why do we use, acoustic emission for, structural health monitoring? Well, a lot of times, we use it for condition ranking. So there may be a time where, a particular bridge, has an issue going on. Sometimes it may be, a very large crack. In the future, they plan to do some type of repair or rehabilitation of that area. So, in the meantime, we can go in, we can monitor that crack to look at activity before the repair is done. Then once the repair is in place, we then follow up and monitor for like an additional 30 days to 60 days to make sure, that repair is working. The other benefit is that, with the systems that we've designed, over the years, since 1995, these are industrial components that allows you to, put these systems out in the field and basically have, unintended monitoring. So, once you stick the sensors on the bridge, once you turn that system on, you now have continuous remote monitoring. And if there's any particular damage that occurs, in real time, then the system will detect it and date it and timestamp it and, goes into a file for, additional analysis. One of the other ways that we use acoustic emission is for, larger structures. So one of the case examples we'll talk about here in a little bit is the Woodrow Wilson Bridge. In this particular case, these are tie beams in which, the tendons themselves are buried within the concrete. So visually, and that's never going to go away. Visual inspection is always going to be, your number one, NDT method. But, when you're looking at stuff that's inside, conduit that you cannot see, this is where acoustic emission, has a distinct advantage over other types of applications, is that we can detect in real time, any hidden or buried defects. And especially, when you've got areas that also may be limited, to what you can do visually. And so, yes, a lot of our systems are acoustic emission based, but as John had alluded to earlier, we recognize that, acoustic emission, isn't the end all be all, and that there's other types of information that we can collect, and together, provide better information, to the client. So, if we're, concerned about, pin and hanger bearings that have been frozen due to rust jacking, we can add in, acoustic emission on the pins to look at, any noise that may be generated during rotation, which is what you want to see. But if not, you can put strain gauges, on the vertical truss members and be able to monitor any potential bending that is occurring, due to, improper movement, of that structure. And, the idea is that, between acoustic emission, between these other parametric, sensors that you can take in, if we can keep that, bridge in service longer, then, that's, fantastic. Plus, being able to prioritize, doing some of this condition ranking, there could be, 30 cracks on a bridge, but, 20 of those, that crack may have taken care of the problem, and with the acoustic emission and under the current loading, you might not need to repair or worry about those cracks at the time because those cracks are now benign. And so it allows you to prioritize, your available resources, whether that be maintenance, personnel, or, other types of, planning. And, we do this a lot, working with, industry partnerships. There are times where, we may be the prime, on the bridge, providing the structural health monitoring, as we were on the Caltrans project for the San Francisco Oakland Bay. But a lot of times we're working with industry partners. We'll have engineering firms, that have been out in the field, they've been doing their inspection, and, they come back and say, look, we've got an issue on this bridge, and, we need to monitor it for, the next 30 days or 60 days. Is that something that you can do? And yes, so we work, very closely with companies like, HNTB, AECom, GPI, Parsons Transportation Group, and many others. So now that we've given a little bit of background into it, we're going to go into and talk a little bit about some of the case studies for some of the bridges out there. And so these pictures are actually from, actual bridges and work that we've done. And so the first one I kind of wanted to go in today was the Varina Enon. Originally, this was a joint project with a local university down in Hampton. And what happened is on this particular bridge, there was a tendon that failed and was replaced. And so the university, along with us, we stuck acoustic emission sensors on that tendon to look for potential wire breaks that are occurring in that, that had previously been occurring, just to make sure that, this new tendon was working as designed. But, as part of that process, when we were doing the installation, we always have our eyes open. And it happened to be that in this particular case, as we were running, the sensor cables, into the towers, we had noticed in the saddle area where we were running our cables in, that there was a lot of structural cracking, at the top of the arch. And a lot of these cracks, they looked like they had been around a while. They were kind of stained, they were discolored, had debris in them. And so we ended up having some extra sensors. And so what we ended up doing is putting four sensors on the east and west face of the saddle area to look for any potential cracking that, may occur while we're doing, the monitoring of the rest of that cable. And as it so happened, over the period of 1 year, there was a new flexural crack that developed. And in this particular case, we were using a 3D analysis in real time to detect the propagation and movement, of this crack. And this was something that we actually published in the volume 70 of April 2012 of the materials evaluation. And so, again, that was, a fantastic project. We happened to have extra sensors. Visually, we saw that, there might be a problem. So we said, let's take a look and see what we get. So this was a very fantastic project. One of the previous projects that we worked on was the Pulaski Skyway Bridge. This was a partnership with HNTB. We ended up providing a total of 4 sensor Highway 3 systems, and there was a total of 17 sensors that went on each system. So we had a couple of AE that was put on the pins in this particular place. This was, issues with the pin and hanger movements. We had 3 displacement gauges at the joint areas, 6 strain, a thermocouple, and then we had tilt meters that were put on the piers. Because for this particular bridge, it is an issue with the pin and hangers. And so, if the bridge is not allowed to articulate and move as designed, it causes, different stress distributions, throughout the structure. And so these 4 systems were monitoring those potential changes during this particular time period. We're actually just got another contract with a company called GPI, and we'll be doing strain gauge monitoring of 50 different truss components during the replacement of one of these pin and hanger systems. And so again, this is one of those, integrated systems where we're providing, both the installation services as well as the monitoring. And it really depends on the client. Some of these projects, we may be providing a monthly report. Sometimes it's a quarterly report. It all depends on what the client needs. So one of the things that we like to, to discuss, early on is, what exactly is the client looking for? We don't want to oversell you a system and tell you that you need to monitor the entire bridge, if you only got, 2, 3, or 4, critical areas that really need to be considered. Now, in the next case study, so this was the old San Francisco and Oakland Bay Bridge. In the U.S., this was our largest system to date. So this was a bridge that was built, back in 1936, and, the ADT currently, is around, 277,000 vehicles with about, 10% trucks. And back in 2009, when they were doing, rolling in one of the deck replacements over Labor Day weekend, one of the inspectors was walking down the bridge and looked up and, saw this 12-inch crack in the head of an I-bar. And the concern, of course, is that, there's a large amount of load that's taken in, to some of these I-bars. And so they ended up doing a repair. And then unfortunately, that repair actually failed, 1 month later. And so, this was a repair of the repair. And, at that point, Caltrans decided to put out an emergency limited bid. And so what they did is they went out and looked at all the different companies that could provide structural health monitoring. And as part of that proposal, they said that, they were looking for a technology that could detect a crack as early as possible, anywhere along that I-bar, not just in the head. So the companies, the different solutions, was, fiber optics. We, of course, provided, acoustic emission. And at that point, we got selected. And one of the things that we had to do for, this project is, the part of that proposal was, we had to tell them what size crack could we detect and how accurate could our system be in locating, where that crack occurred. So we said we could detect a 0.1 inch crack within 18 inches. And so as we were selected, basically Caltrans said, well, now you have to prove it. And so working with the University of Berkeley and their CSS structural lab, we had I-bars that were fabricated, and then over 3.5 months, we did fatigue testing and ended up generating a crack, in one of those I-bars. And we used the same system, we used the same sensors and the same type of setup that we were going to, be using on the bridge and what we had proposed. And we were able, within the first 3 weeks, we started detecting, AE at a particular location visually, and also using UT and dye penetrant. You couldn't see anything yet. We continued to, fatigue the structure, and we were able to detect the crack initiation at 0.07 inches and with 0.7 inches depth and about 1.25 inch down of a 2-inch thick I-bar, and we were within 2 inches. All of that had to be validated by, Caltrans personnel. And once those results were validated, we were then allowed to put this on the bridge. So in the end, we ended up with a total of 16 systems, 8 systems on the north side of the bridge and 8 systems on the south, and 640 sensors monitoring 384 I-bars. And so, if you do the math, that ended up to about 1.67, sensors, per I-bar. So this is, again, where, using the ability of acoustic emission and using a different frequency sensor, we were able to have sensor spacings of 35 to 50 feet and was able to detect, a crack in that eyebar. And what was nice is then 1 month later, after the system had been commissioned, we ended up getting a cluster rate alarm that was automatically generated by the system. This notification went out to both MISTRAS personnel as well as Caltrans. By the time I got done taking a look at the data, I got a call from Caltrans and they said, look, do we need to go out and take a look at this? And I said, yes, this is something that needs to be addressed. Within about an hour, they were out there on the bridge. Visually, they were walking up and down, and the system and notification told them exactly what system it was coming from, so we knew which section of eyebars. The system would tell you exactly which eyebar that the activity was coming from, and not only that, it told them the location. And so what they ended up doing is walking up, because initially visually they didn't see it, but when they pulled this conduit away from the eyebar, that eyebar had worn away about a 1/8 inch, section of steel. And honestly, that doesn't seem like a lot. But when they went back and did an internal, investigation, had they lost about another 1/8 of an inch, they would have had something similar that would have created a stress condition that was similar to what initiated that crack, back in 2009. And so, within a month of the system going live and being commissioned, the system detected something, and, the end result was that it paid for itself. So the other current project that we have going on right now, we're 2.5 years into a 10-year project on the Woodrow Wilson Bridge. This is a post-tension structure with V-piers. At the top of these V-piers are big masses of concrete that have two tie beams in between them. And so we are monitoring 72 V-piers, about 138 tie beams across all V-piers in the bascule section, looking for potential wire breaks. And the reason is that, it was one of these bridges that may not have received some, bad grouts from many years ago. And on some of these other bridges that had been identified, they were starting to see, corrosion, at the 5-year mark. And so both Virginia and Maryland SHA wanted to be proactive to keep an eye on this because it is, a busy bridge. And so we're now monitoring this bridge for the next 6.5 years. And we do about 4 visits per year as needed. We provide yearly maintenance. And the data service, and then this also is on a quarterly basis in terms of reporting. The last case study before I turn it over to John to finish up with his, as Matt said earlier, we're now on the George Washington Bridge. This is going to be a 7-year contract where we're going to be installing acoustic emission sensing along the main cables starting on the north and then switching to the south, as well as both the anchorages. So for this particular project, we'll be looking not only for wire breaks in the main cables themselves. We'll also be looking at the temperature and humidity of the dehumidification systems that are going to be installed in the anchorage, and be able to look for any potential wire breaks down there, and to make sure that the dehumidification is working as designed. So at that point, I'm going to turn it back over to John Watson out of the UK so he can talk about the Hammersmith.
Thank you, Richard. I'm just going to move the slide one on. Okay, so for those of you not familiar with the Hammersmith Flyover, it's one of the main arterial routes from London's main airport in the west of London to central London. It was built in the 1960s, a segmental segmental precast post-tension box girder, which is basically pulled together by a series of tendons that are threaded through the center box girder. It's quite a special bridge, as it was designed with fairly revolutionary in-deck heating to eliminate the need for de-icing. However, over the years, that system had been decommissioned and turned off, and it was carrying a significant amount of traffic and became subject to a variety of investigations and suspicion about its performance. Unlike many of the bridges that Richard has mentioned, luckily for us, structural failure is relatively rare. Even significant defects are relatively rare in real terms. Hammersmith Flyover, however, was quite unique. By the time that MISTRAS became involved, they were already finding fairly substantial defects within the structure with fairly basic inspection, and the bottom of this slide shows severe cable corrosion for these post-tension cables that were passing the entire length of the viaduct. The problem to the owner was how severe is this cable corrosion, how many wire breaks do I have, and where exactly should I be looking for wire breaks. These cables, like many post-tension systems, were encased, in this case in mortar, which totally obscured any defect and deterioration unless you physically broke into areas of the structure. The actual anchorages of these tendons as well were obscured and difficult to reach in very highly reinforced areas within the structure. MISTRAS were able to monitor with acoustic emission the entire length of the viaduct to detect wire breaks as they occurred. We also measured the segment separation with very sensitive displacement gauges down to plus or minus 2.5 millimeters to detect separation of the segments as the post-tension was released. We also had a number of automatic total stations on the inside of the structure, quite a rare solution due to third-party land ownership issues on the outside, that measured the physical sag of the structure at mid-span. These systems were installed in 2012, and they continued to run for several years, and we detected a very large number of wire breaks throughout the structure and a variety of different other structural faults. This information all enabled better asset inspection and better asset management as they completed the inspection, which led to the very sudden closure of the structure on the UK's Black Friday, which is the last Friday in December before the holiday season, which caused some 80,000 vehicles to have to divert through the local streets rather than on this main arterial route. So the next few slides show you some of the design and construction of this very large monitoring system. So in the inside of the flyover, you've got about between 3 and 4 feet of headroom with acoustic sensors mounted on the outside cell and on the floor. These are underneath the small metallic brackets that you can see with the black cables running back all the way to the monitoring systems. And it's these microphones that were able to pick up the fracture of wires, differentiate this sound from other traffic sounds as the traffic's trundling across over the top, and then process the signals and tell you if they're wire breaks or not. So as part of the process to build our neural network, our artificial intelligence within the system that processes these signals, we had to carry out a series of mapping exercises. So once we'd installed the sensors throughout the structure, we made a number of clicks with a spring-loaded center punch, like a miniature version of a Sharpie Schmidt hammer, which you can see. These clicks were correlated with the physical position on the actual duct, and this enabled us to make a sound map of where the clicks were made and where they were physically detected. So we were able to make a unique map of how sounds travel through the structure. And this meant that if any similar clicking sound occurred, we were able to cross-correlate with our calibration with a high degree of accuracy to tell you exactly where the wire breaks occurred. The system itself went through a very stringent factory acceptance test for proof of operation, but it also went through a site acceptance test where the customer broke open one of these many ducts to reveal cables, and there's an image that you can see with a small section of tendon exposed in the center. The cable inside, or one of the individual wires, was progressively thinned with a small rotating hobby wheel, a bit like a small grinder. And this created a very distinct signature sound that the system detected, but processed away because it was not a wire break. And you can see the long grinding sound of the spinning wheel. Over the period of the blind test, further sounds were detected, and eventually the wire microfractured and then bang, snapped. In this image you can see the actual wire itself. Once it's broken, you can see a bit of shiny polished metal where the metal had been ground, and then a small crack, and about 1 millimeter of wire extension. This represents quite a realistic example of wire break. This wasn't removal of a wire from a bundle and snapping. It was a natural break after an induced defect was put into the tensioned wire. So when the wire actually broke itself, we got a very distinct snapping sound that you can see in the transient. This was automatically detected, prioritized by our neural network, and placed in a separate data file. We were able to get an email to say that a suspected wire break, I should say, had been heard, and that enabled us to do analysis to our MISTRAS proprietary procedure that enabled us to identify the exact position of the wire break, both in length but also in cross-section. And in reality, that was actually confirmed to within 10 centimeters of the actual break itself. So 10 centimeters, about 3 inches, accuracy over 600 meters. And the way that this is then shown to the customer, this data was loaded onto a website, and then the position of the wire break shown in cross-section with the arrow showing the duct position, and then a longitudinal position, again identifying this position. And this information from the initial installation and through the monitoring all the way up to the closure enabled the inspection engineers, rather than doing random breakout to look for broken wires, it showed them exactly where the problem was, both the extent but also the exact position. So every time they carried out an inspection, it was a lot more efficient and a lot more focused. And this caused this sudden increase of information through destructive testing that made them force them into the situation where they had to close the bridge. After the closure, which isn't really covered in these slides, the monitoring continued throughout the construction process as a safety tool, and then the system was completely reconfigured to provide long-term structural health monitoring on bearings, flooding, crack monitoring, and a bit of residual monitoring just to make sure the original post-tensioning was fit for purpose and did its job. So this is the last of our case studies, a fairly extreme case study, and showing kind of the value of monitoring for structures at the very end of life, just prior to rehabilitation. So in these next few slides, it takes us through the last few conclusions. So all of bridge engineers nowadays really have quite significant challenges to assess structures, particularly aging structures, often with hidden defects, often with hard to inspect areas. It's very difficult to confirm the true condition of a structure and also to manage it safely. Inevitably, these existing assets with budget constraints, there's even more pressure to maintain these well beyond their original design life, with ever-changing conditions, with significantly increased numbers of traffic, reduced maintenance periods, shorter and shorter opportunities to intervene and get information back, but also budgetary pressures to reduce maintenance as well. So structural health monitoring and acoustic emission are very powerful tools that enable bridge owners to get a wide variety of performance information about how the structure is reacting to load, whether it be dynamic loading from users or environmental, but also in getting information about different defects, both in the detection stage, but also how defects and deterioration is occurring and progressing. The two factors enable bridge owners to better understand the structure and then predict when maintenance is required, rehabilitation, or even replacement, and also how to protect the road users and other third parties. So in conclusion, I hope you've enjoyed this presentation. We've attempted to show you a little bit about MISTRAS, about our range of different solutions from the inspection side, non-destructive testing that we touched upon briefly. We focus mainly on products today, our structural health monitoring products and services. A little bit of an emphasis today on one of our unique technologies, which is Acoustic Emission, and looked at its application in wire brake, on post-tension structures, cable structures, but also on a variety of applications, monitoring for cracking in concrete and also cracking in steel structures. At this point, really, we'd like to open up, I think, to Matt, just to get any questions from anyone on the floor. Thank you.
Sure, thanks, John. We have a couple questions here. First is, do you have a method to monitor rust corrosion? John or Richard?
So in terms of corrosion, we have used AE in different types of projects to look at corrosion, but we need to preface this that, when we're talking about being able to detect corrosion, it needs to be active. And so, if you're doing, testing, on a bridge where you suspect that you've got, water inside the tendons, or if you're looking at a parking garage, it needs to, we need to make sure that corrosion, is active. And a lot of times if we're doing it, on bridges or other structures, we need to do it at a time where we can lower the threshold. Because, if you recall, earlier in the slide, when you're looking at absolute energy, corrosion is on the lower end, of the scale in terms of, amplitude and energy. So in that particular case with the software, we can drop, that threshold of the system and make it extremely sensitive to those types of corrosion processes. And I actually did, another test for another project, looking at, cracking and tie rods. And in that particular case, we had the ends of those rods inside a corrosion bath. And so, while we're looking for detecting cracking in those tie rods under load, you could see the active corrosion that was going on at the time. So yes, there is a process, in place, but, the method and the timing and when you do this is a lot different.
Great, thanks, Richard. We got another one here. Does the system detect wire breaks only when it breaks, or does it pick up acoustics as the broken wire rubs against other wires?
I'll jump in and take this. A very good question. Acoustic emission can detect rubbing and friction, but the way that the systems are often deployed for suspension bridge and cable stay monitoring, and indeed post-tension structures, the system is really designed with the sensors with large separations far apart. So it's really designed to pick up only the larger signals from wire break. So fretting of signals from wires rubbing may be detected by local sensors, but are insufficient to be detected by multiple. So generally they're ignored and removed. So a bit of both, but predominantly we just detect wire breaks.
Great, thanks, John. Another one here, cable stay bridge condition. With the collapse of the cable stay in Italy, have you had any suggestions or ideas to help me as an owner to gain information in that area?
I'll take this one and maybe hand over to Richard to see if he's got any further comments. I mean, this is particularly of interest to us. Inevitably, there's been questions about corrosion detection, and that's really the precursor to wire break. And Acoustic Emission can, as Richard said, detect corrosion, but typically we use more non-destructive testing for that. So we've got experience doing radiography on cables inside concrete and inside ducts that can identify surface discoloration from corrosion, but also detect wire break that's from wires that have come out of the bundle, also detect voids in grout and discontinuities in grout that may let water and other moisture in, which again leads to corrosion. And that's typically done with digital radiography. The other thing that you can do is shoot ultrasonic signals up from the end of a cable. Not always possible, but on cables, some cable stays you can. And that will inspect individual wires for breaks and section loss up to about 3 or 4 feet from the base of an individual wire inside. And that's often the critical area where corrosion occurs as the water runs down. And then longer term, acoustic emission will give you a very good indication of wire break occurring, and then other sensors, accelerometers or some forms of strain gauge strapped to the cable will give you information about cable fatigue, cable vibration, from which the data can be computed to give you an estimate of fatigue life and also indicate whether the cable is behaving as you would expect it to. So there's a couple of different ideas and solutions that we have, but it really also depends on the structural form. Have you got any other ideas, Richard, or comments?
Nope, I'm actually, in agreement with you. So yeah, the tough issue, of course, is corrosion. And we do have a product that, is designed, it's called CorePack, but, it was originally designed for, a different type of industry, simply because, we're not dealing with, the other types of, background environments and stresses that you may see. But, and with regards to Italy, there's, I'm sure over the next couple of months, is the information with regards to, what the mechanisms was. It looks like it was, potentially corrosion, here, and these tendons were actually, encased inside of concrete. So as John mentioned, there could have been, some initial, or there could be, some initial work done with the radiography, and then based on what was observed, then could have gone back and mounted, with acoustic emission, to, look at potential additional degradation over time. But, at this point, it's really hard to tell, or it's really hard to say without, the full analysis being done yet.
Okay, I think we have time for one or two more. I have a good one here. Some literature suggests that AE is only effective about 80% of the time and therefore should be paired with strain technology to reduce the false positives. Any comments, guys?
It's a great question. Richard,
go ahead, John. Well, I'll let you start out first, and then I'll follow up.
Okay, thanks. I mean, as with any technology, it's not the technology that fails; it's the application. So I think if the damage mechanism is very well understood, and the attenuation, how far the sensors can be apart, is understood and measured. So you've got enough sensors to detect the source, and if you're monitoring during the period of activity, so if you monitor for just one day for wire break, you're going to be very lucky to detect something or unlucky depending on your view. So the monitoring period has got to be suitable. But certainly any monitoring technique, the reliability is going to be increased in terms of the analysis if you're looking at other data simultaneously. So whether it be strain or temperature or other forms of environmental loading input, you can cross-correlate acoustic emission with that. For instance, if you get cracking and there's no strain on the structure, or if you get an acoustic signal and there's no strain on the structure, it's very unlikely to be cracking because there's no load on the structure. So you can use things like strain to increase your confidence beyond 80%, I would say. Richard?
Yep. No, I mean, I'd agree with that as well. Because keep in mind, a lot of these, methods that we talk about in sensors, they're designed to be complementary. The benefit with acoustic emission is that, if you're looking for, crack initiation, like if we go back to the San Francisco-Oakland Bay Bridge, we were able to, detect a crack at, 0.07 inches. Unless you happen to have a strain gauge right there at the tip of where that thing formed, they would have to grow significantly large before you'd see a significant change, in the strain to alert you, to a potential problem. And so, that's, one of the benefits with AE is that, on this bridge and because of the load, we had great wave propagation. And so we were able to have, larger sensor spacing. So we could minimize the number of sensors required to monitor, these, 60-foot, 65-foot long, I-bars with 2 sensors. You didn't have to have, 25 strain gauges or 50 strain gauges. But, this would be one of those applications to where if, Acoustic Emission did see something, this is an opportunity to go in and follow up. Maybe you add a strain gauge, or, depending on what the mechanism is, you add, another type of parametric. So, again, there are, advantages and limitations. And so you want to have the right tool for the job.
Okay, thanks, guys. I think that's about it.
Great. Thanks so much to Richard and John and Matt for their presentation. That wraps up our questions and this webinar. Any questions we were unable to address will be answered offline. If you haven't already registered for the upcoming Roads and Bridges virtual trade show on October 10th, you can do so by going to www.roadsbridges.com. There is a section under the Events tab where you can access the registration page. This event is virtual, free, educational, accredited, and best of all, there is no traveling required. Please stay logged in after you hear the webinar end to receive your PDH certificate for this webinar. You will be linked to a form with spaces for your name and email address. Please fill the form out with your name as you would like it to appear on your certificate. The email entered should be the one with which you registered. The completed certificate will appear on your screen, and you can then print it out for your records. For those of you using the multi-viewer form, please allow up to 2 weeks for delivery of PDH certificates. On behalf of Roads and Bridges and our sponsor, MISTRAS, I would like to thank everyone for their participation. This webinar will soon be archived at the same URL you used today, as well as on roadsbridges.com. So long, everyone.